about a topic that I've been working on with a number of very dear collaborators for a couple of years now. I want to kind of report on this general problem of fluid stabilization in cosmology. And so we have reached a few results that I want to present today, and but there are still many open problems. So I hope that this is also interesting for some people, maybe to pick up one or the other of those problems and contribute to this interesting topic. So let me maybe maybe first say that anything that I will discuss today that is new, any new results, is a joint work with always a subset of these collaborators of mine, so Todd Olenek from Monash, and Zoe Wyatt, who's now a faculty at Cambridge since recently, and then our PhD student Maximilian Offner here from Vienna, who's jointly supervised by myself and Zoe. And these are the three papers that you can see here that the new results that I will present today are based on. So let me maybe put this in, give you the mathematical context. So anything rigorous I will say today is related or based on the study of the Cauchy problem for the Einstein fluid equation, so the Einstein-Euler system, and it's based always in cosmology. So we're interested in cosmological solutions. Okay, so that's the mathematical context of today's talk. But I believe that this topic also has a interesting, possibly an interesting implication for physics. This might be still vague, but I think it is an interesting motivation, which I will mention also in a second. So what we're basically interested in to study the future long-time behavior of the Einstein-Euler system. You can see here that the Einstein-Euler system is given by this set of equations. We have Einstein equations. And then when this is the way we define the energy momentum tensor with a fluid density and the pressure, then the divergence, the fact that the energy momentum tensor is divergence free, implies this coupled first order system for these variables of the fluid, where u is the fluid velocity. And when we see that we have here not enough equations to find a unique solution, so what we also need to impose is a so-called equation of state. And this equation of state captures, let's say it briefly captures the features of the fluid. We will mainly consider a linear equation of state. I'll get to this in a minute. Okay, so that's the mathematical framework from the equations side. And when we look at the, let's say, background spacetimes, or if we look at the regime and where we want to study solutions to that system, then we want to do this in cosmology. So we always have some spatial manifold M. I should put here a 3. I will talk today exclusively about 3 + 1 dimensional spacetimes. We have a spatial geometry, which you can consider as so-called rescale geometry, because in cosmology, in the general case, we always have spacetimes of this form G4 here, where GAB of t is, let's think about it as an expanding metric, where that is always of the form A of t square. So A is called the scale factor, just a function of time that is monotonically increasing, let's say, for the purpose that we are interested in. Then we have a fixed metric G0 on this compact manifold. And now the scale factors that we will consider today mainly are either exponentially expanding. Those are ones that where a lot of results are known in the literature. And then we'll look at the so-called power law inflation. That's more the case that's interesting for the results that I will discuss today. Okay, but I will repeat all these things on the following slides. This is just a slide where you can see anything that will play a role today. Okay, so what are the problems that we can study for this system? So as always, we can study kind of a toy problem, where which I call here case A, the linear case, where we fix the space-time. So we take a given cosmological space-time with a fixed expansion rate and a fixed spatial geometry, and on that space-time we study the relativistic Euler equations. Anything that, when I couple to Einstein, is always, I always mean relativistic Euler, right? So even though sometimes I say Euler. This is the case physically that has no back reaction. So the space-time does not feel what the fluid is doing. But we can sort of study what the fluid is doing by itself and see if it forms any singularities or whether it remains regular. And also whether it remains, let's say, close to homogeneous data if we start with homogeneous data. That's one problem that we can study. And usually it serves as a precursor for the actual problem that we want to study, namely the nonlinear stability problem, where we do couple the Euler equations to the Einstein equations. And so we have a mutual coupling. And so a possible bad behavior of Euler equations might also couple back to Einstein and vice versa. Now, in this context, there has been an interesting phenomenon observed almost 30 years ago, rigorously. I guess it was known probably before, but the first rigorous result is almost 30 years old, which is this phenomenon of fluid stabilization. So we know that generally Euler equations do form shocks in the classical regime even. And as I will mention soon, also we have some rigorous results in the relativistic literature. But this fluid stabilization effect says the following. So if background space-time is expanding sufficiently fast, in that case, no shocks form if the initial data are sufficiently close to homogeneity initially. Okay, and that the solution is then future globally regular in time and in many occasions also remains close to homogeneity. Yeah. This is an interesting effect. We'll maybe talk in a minute about why this is interesting for physics. It's an interesting effect because you can think about it as a playground to say, well, now I can start to manipulate the parameters. I can maybe change the behavior. I can change the nature of the fluid a bit. And I can also change the expansion rate and see where shocks start to form, or what is the regime where things remain regular. So what we would like to understand in general is under which conditions on the space-time and the fluid, meaning expansion rate and, for instance, speed of sound, which will be the parameter that we will consider here, are future developments of initial data which is close to homogeneity, future complete, future regular, and close to homogeneity, right? So this is the question. When does this fluid stabilization occur? Why is this interesting for cosmology? Again, I consider myself rather on the mathematical side, but I think one can interpret this in the context of open problems in cosmology, where on one hand, we do see that the universe today looks very homogeneous on large scales. So after a long evolution of the universe, it seems very homogeneous and isotropic. But on the other hand, there are structures that have formed on some smaller scales, and maybe they formed from initially homogeneous configurations. So the question is, how can this happen, right? Because we know about many stability results in cosmology. How can sort of matter concentrate in some regions? How can we study this problem from a mathematical point of view? And so in the context of this Einstein-Euler problem, some people have said, and again, I think one can debate about this in the nature of how we interpret those shock formations, but one way to model structural formations might be that actually if you have a shock that forms in such a fluid during the cosmological evolution, that might be when your model literally here starts to break down and maybe some other structures form that you cannot model anymore as a fluid. And then the question would be, well, let's assume that might be the case, or maybe shock formation can be interpreted as another interesting physical effect during the cosmological evolution, maybe shortly after the Big Bang at some point. Then you would like to understand, okay, what is really the necessary condition from a rigorous mathematical point of view for this shock formation to occur? Or on the other hand, how can you rule out shock formation by knowing that the universe, for instance, expanded extremely fast and suppressed it by this fluid stabilization phenomenon? So my aim or let's say our aim from the people that I've been working with on this problem would be to provide some rigorous bounds in the parameter space of the problem, namely, for instance, for the speed of sound of the fluid and the expansion rate, for the fluid to be regular, future globally regular in time, or on the other hand, for shocks to form. Yeah, so we'd really like to understand what are the conditions during the cosmological evolutions that allow for shock formation or that really suppress shock formation, and putting the bounds, making the bounds on this sharper than the ones that we knew before we started to work on this problem. So, as we know, there's a huge zoo of solutions to Einstein equations. What we will do today is we will try to discuss this in the neighborhood of the standard cosmological solutions, the standard homogeneous solutions, namely the Fajman solutions. So we'll always consider a perturbation, or if we consider the problem on the background, then a really homogeneous universe that has roughly this form here. Where, as I said already, so GIB is a fixed metric on our spatial manifold, and then we have a scale factor A of t, which models the expansion. And then when we want this solution to be isotropic and homogeneous, then we know that our spacetime has to have one of those, has to be, well, there are some exceptions, but let's say for now, it's fair to say that it has to be either of negative curvature, so like some quotient of the hyperbolic space. If you want to have it compactified, I like to have the universe compactified, no boundary, or you consider the torus, or you consider the S3 with the corresponding constant scalar curvature -1, 0, and 1. And for the fluid variables, to respect homogeneity, so we have our fluid variables to only depend in that case on time, not on space. When we plug those things into the Einstein equations, and Einstein equations reduce to the Fajman equations plus the continuity equation for the fluid. And when we look for solutions, or when we look for asymptotic solutions to this set of equations, we find a number of standard models. Before we do this, as I said, we need to restrict the class of fluids that we work with, because the fluid equations themselves are insufficient to be solved. I mean, they're not complete. So we have to impose an equation of state. There are many equations of state one can impose, but the most standard one in cosmology would be a linear equation of state. So P here is is K times rho, and K is between 0 and 1. And in this regime, you can already discover different behavior of the fluid. So for different Ks, that really changes what the fluid is doing. And this K corresponds to the square of the speed of sound. So that's the way I can think about it. If K is 0, then we get dust. If it is somewhere between 0 and 1/3, we call this a regular fluid or a massive fluid. 1/3 is radiation. Between radiation and the stiff fluid, which is K equal to 1, these fluids have no name, but you can also put this K there. We will not consider this case. We'll mainly consider this regime between dust and radiation, including dust and radiation in this talk. Okay, so in this homogeneous setting, we can immediately integrate the continuity equation. We obtain this interesting relation that gives us the following. So the energy density of the fluid density decays depending on this parameter K with the scale factor. So if, for instance, we put K equal to 0 as for dust, then this decays like 1/a⁴. And when A is, for instance, T, like in the linear expansion case, then this is exactly what we know for dust. By the way, this is also what we know for Vlasov matter, because that's what dust, so Vlasov matter approximates dust towards the future in the expanding regime. So this is all consistent with what we know. And then the Fajman equation takes this particular form, which then we can integrate. And now if we put a few parameters, we'll fix a few parameters, decide, for instance, on what topology we want to study this, with what curvature, or if we have a cosmological constant or not, then we get different solutions. And I've put here some canonical solutions which are interesting and relevant for this talk. So first of all, of course, we have de Sitter space-time here, where we have exponential expansion caused by the cosmological constant. There are corresponding solutions which also have exponential expansion for other spatial topologies. essentially for any spatial topology, you can create such a exponentially expanding solution. Then we have a very interesting solution, which is this so-called Einstein de Sitter solution, which one should not mix up with the de Sitter solution, because the Einstein de Sitter solution is a slowly expanding meta-dominated solution, which exists on the torus. So we have the 3 torus. And then if we couple the fluid with a linear equation of state, then you see that the expansion rate here depends on this parameter k. So the spacetime expands depending on what k actually is. In any case, it expands slower than the linear case. That's important here. Then we have the Mill model, which is curvature dominated. So the matter here is not dominating how the spacetime expands. In all these cases, by the way, the cosmological constant has to be 0, because if it's not 0, then we get a de Sitter-like behavior. It dominates everything else. And finally, we have, if we put the sphere, then so positive curvature, then we get a recollapsing universe, right? So there we don't even have a complete end of the universe, so we cannot really study the problem that we want to study. So we will focus more on these eternally expanding models, but I will get to those. Get back to those in a second. So again, in the case of lambda 0, this is a point I want to stress. I think it's known to everybody, but I think it's still important to emphasize here in this context, is that the future behavior of spacetime depends crucially on the spatial curvature. If you have negative curvature, you have eternal expansion. If you have positive curvature, you have recollapse. And if you have vanishing curvature, then the meta takes over and dominates and gives you the expansion rate that I just showed you on the slide before. Yeah, so that's the interest. That's the reason why I find, from a mathematical point of view, it interesting to study the lambda equals 0 case, because the future behavior of the universe really depends on the details. In contrast to the case of a positive cosmological constant, where everything is dominated by that and the curvature is essentially irrelevant. Okay, so what can we study now? Get a bit more to the details. So what are the problems that we can study here? So we can study the classical nonlinear stability problem towards the future. So we take a cosmological constant, a cosmological solution, and if that is a vacuum solution, we can interpret it as a solution to the Einstein-Euler system, a trivial one, and then we can perturb it in the set of solutions to that system and see what the future development of our perturbation does. Then I say we can study this toy problem, where we fix our background spacetime and only study the Euler equation on that spacetime. That problem is interesting as a precursor for the actual nonlinear stability problem, but it's also interesting for another reason, because we can study solutions that are actually not solutions to the Einstein-Euler system. Remember, when we take the Einstein-Euler system, then I just showed you a couple of solutions, right? So the torus, for instance, with a, let's say, linear expansion rate is not among those solutions. So we cannot study its nonlinear stability, right? In this toy problem, we can just take that solution because we want to make our life simple, take the torus, take a nice expansion rate, and then we can just study it. That just works in this linear problem. And another simplification that one can do, this little sidestep is not that important, but what one can do is one can consider irrotational initial data. In that case, the fluid equations reduce to a wave equation, and so we can study the behavior of the solution with techniques that are more familiar, let's say, right? So that's a simplified technical reduction of the problem, which we can also study, and in some cases it has been studied. So I just want to put this out here. Okay, so what do we know about problems like this? Again, there's been many results before. There were many results before we started to work on this problem. So that shocks can form in fluids is known for a very long time in classical fluids, which are the non-relativistic limit of the equations that we study. And very naively, again, in this talk here, I will not demonstrate any result on shock formation. I will demonstrate results on non-shock form, as well, that shocks do not form. But nevertheless, the shocks that have been shown to form are of this type. So we have some velocity profile here that we start with is t equals 0. This profile evolves and finally at some point, at some finite time, develops a singularity in the first derivative. That's kind of a one scenario how one can think about the shock formation. And actually the first instability result in the context that I discussed is quite old, which is this famous Oppenheimer-Snyder result from 39, which, if you put it in this context here, shows that Minkowski space is unstable for the Einstein dust system. Remember, dust is the case where k is 0, the speed of sound. And what they have actually shown that Minkowski space is unstable. A more, let's say, sophisticated result also on instability is by Christodoulou from 2007, where he shows that on Minkowski space, if we take a quite general class of relativistic fluids, from arbitrarily small data, it forms singularities. That belongs in the category of linear problems that I discussed. We fix the spacetime, we study the Euler equations on the spacetime, and we have shock formation from arbitrarily small data. Now, in our context, we want to do cosmology. So actually, we want to consider expanding spacetimes. So we can say Minkowski space is technically also a expanding spacetime, just with a of t equal to 1. So it's actually not expanding, but it has, let's say, constant. The expansion is, let's say, here's a of t is 1. Okay, so that's the one how we can think about it. And how we can interpret this now is the following. So we can say, okay, if the spacetime is not expanding at all, shocks do form. So on the very extreme side, we know that in the relativistic case, shocks can form. Okay. Now, the first result, which I mentioned at the very beginning of this talk, that got this whole idea started, is by Brouwer, Rendell, and Reula from 1994, where they studied this is even a more, let's say, more of a toy model, where they studied this Euler and Newton Cartan system, so a Euler elliptic system, where they showed that if you consider solutions that have a cosmological constant, one can implement this there, so you have exponential expansion. That's the main important point about this. Then, if you study this problem for a certain equation of state, then small perturbations will lead to solutions that are future global in time. So that was the first result, where they showed that the Euler equations indeed remain regular if the spacetime is sufficiently fast expanding. What they also showed is that we take dust and actually look at this corresponding solution to this Einstein de Sitter solution that I showed you, the slowly expanding one, a of t is equal to t to the 2/3, then we have shock formation. So that is kind of unstable in the context of this elliptic coupled to Euler system, right? So that was the first hint that something like fluid stabilization actually does occur. And then the first result for the Einstein-Euler system, which rigorously established fluid stabilization, this context was by Rodniansky and Speck from 2009, where they considered now the exponentially expanding case. So they had a positive cosmological constant. To be precise, they emulated this constant by a scalar field, which is something that Hans Ringström sort of set up initially for problems that he studied. So if you take a scalar field with a suitable potential, then the spacetime that is a solution to this Einstein scalar field system expands exponentially. So you can use this as a playground to study this coupled to other matter systems. So this is what they did here, and they showed that that for irrotational initial data, indeed any sufficiently small perturbation leads to a future complete solution. So there's the first case of fluid stabilization. Very briefly, just to see how this effect is visible in the equations, you can do here. If you look at this equation, you see that on the right-hand side, if you rescale the system appropriately, then the fluid equations here or the equation for the fluid potential, which, as I said, in the irrotational case is now a wave type equation, they have some dissipative terms on the right-hand side. And these are exactly the terms that enable them to prove that that the solutions to the system are globally regular. Okay, that's basically where the expansion rate of the space-time is visible in the equations. So what we knew since then is that exponential expansion can cause fluid stabilization, even in the presence of back reaction to gravitation. And since then, this exponentially expanding regime has been studied extensively. So Speck eventually removed this assumption on the irrotationality. Löbe and Valente-Kohn proved the same for a radiation, so fluids where K is equal to 1/3. And there are plenty of other works that improved on these results by Lefloc-Way, Hadget, Speck for dust, Olinik, and also Puska-Mondal is in the audience here. So what we can conclude about this regime of exponential expansion is that in quite general scenarios, fluid stabilization occurs. So exponential expansion is sufficient to regularize the fluid globally. Now, of course, we would be interested to see what happens when we have a less dramatic expansion, so a slower expansion. That's sort of the next question. We want to push it more to the side where the universe is expanding slower. So let's go to power law inflation. Power law inflation, again, we have the same type of space-time here, but now A of t is some t to the 1 plus delta, where delta is positive. That's usually what you refer to as power law inflation. So you have something that's a bit above linear expansion. And the nice thing is now if we fine-tune our delta, we can also fine-tune it, let's say, to 0, and then we get linear expansion. So that is a nice transition, let's say, here in this parameter delta, where we can go from the accelerated expansion, which is power law inflation with delta bigger than 0, to linear expansion where delta is 0, to decelerated expansion where delta is negative. Okay, so we can really look at this interesting transition. Remember again what I said before is that if the space-time is does not undergo accelerated expansion, as for instance caused by a suitable scalar field, which emulates the power law inflation, that you can do the same as you can do for cosmological constant. When a spacetime is expanding accelerated, then the global topology of your spatial manifold for homogeneous data is not relevant, okay? Because the Einstein flow localizes, which is this famous result of Ringström. So exactly at this sort of threshold of linear expansion, something very interesting happens to the Einstein flow, and we want to see here what happens now for the fluid. Now, okay, this is exactly what I said, right? Yeah, so we can really go, we can really change between these regimes. And there's a result by Jared Speck, who studied exactly that regime of power law inflation on a fixed background space-time that is expanding. But again, that is in my estimation, I guess, not the main point. I think he could have also proved the same result with back reaction. Yeah, I think it's just once we understand this problem, we can see easy how we can put in the Einstein equations into the scenarios. So I think here the fact that we have without back reaction is not so important, even though I think it has never been done, from what I remember, rigorously. But let's talk about this result here. So what he showed is two interesting aspects. So the first thing is that if we have a fluid in a power law inflation universe, that meaning it expands accelerated, delta is bigger than 0, then the fluid stabilizes. So that means we do not need exponential expansion. Power law inflation is enough. But remember, this is still accelerated. So the point here is that it's still accelerated. That's what makes the that's what makes things work. Now, if we go to the linear expansion rate, we see where I put here this this red sign, and we consider radiation, then we have shock formation. So he proved that shock formation here by translating this scenario into Christodoulou's result by a conformal transformation, and showed that actually when you go from accelerated expansion to linear expansion, you do have shock formation. So that's interesting. There the fluid really changes the behavior. And remember also the Einstein flow changes behavior exactly at this point. Dust itself is much more regular when it comes to the global behavior. Dust even stabilizes when you go to T1/2 plus a little delta. Yeah. So I will put all this in a big picture in a second, so we don't have to remember the details. But the important thing is that we have shock formation on the threshold of linear expansion. The important points, what we see here is that for the stabilization results, so the first of his results, it was important not that we have power law inflation, but actually was important that the integral over 1 over a is finite. And you see that this scenario, that this condition is violated once we are at a of t equal to t, then this is not finite anymore, so this method breaks down. So something interesting happens there. Now, when we look at this result, of course, the question is, okay, but what happens for the other types of fluids for linear expansion rate? And maybe what happens when we have back reaction for the linear expansion rate? Because there things seem to get interesting. Again, I already said, but I want to emphasize it again. So the first appearance of a fluid instability here for radiation occurs for the threshold of linear expansion rate, which again is the point where the Einstein flow becomes non-local. Yeah. Good. So let's look at what I just discussed here in a picture that makes it a bit more simple. So here I like to think about this in the following way. So here on the vertical axis, I put the speed of sound, or k, which is just the square of the speed of sound. And here, this red line is the radiation line. Okay, this is where radiation occurs. And here on the right, I put expansion rate. And this bracket here is not very accurate. I mean, everything that is right of alpha equal to 1. So alpha is now, I should have written this, a of t is t to the alpha. So alpha is now, here it's 1. So that's the linear expansion rate. Right of this, so everywhere here we have accelerated expansion. Left of it, we have decelerated expansion. Okay. So what do we know? By Speck's result, we know that everywhere here to the right, we have stabilization of the fluid. In this case, so far without back reaction, but as I said, it would also work with back reaction, I'm pretty sure. Here we have an instability point. Yeah, so for radiation, for the linear expansion rate, there we have instability. But on this line here, we don't know what happens. So for any regular fluid, we don't know. But for dust, we also have stability. And the stability for dust goes all the way to the slow expansion rate here. Okay, so anything on this line, except for these 2 points and left of it, is open. And we would like to understand what can we contribute to understand about this region. So this is essentially what I will discuss today. So I want to talk about this line. Okay, so I want to go to the let's say transition line between the accelerated to the decelerated regime and see what we can prove there. Okay, so that's basically what all the 3 results that I will present today concern. So this is the fluid stabilization in the regime of precisely linear expansion. Okay, so the first result that I want to show concerns this line, this red line here, where we proved stability first without back reaction, just on a torus. So we have a linear expanding torus with A of t equal to t, and we will show that on this space-time fluids remain regular if we start with sufficiently small initial data. That's the result that sort of started this whole project with Todd and Zoe together. Actually, we started this right before Corona. That's how far this goes back. And what we show is essentially what I just said. So first we take the irrotational case, just for simplification. We consider a linear expanding toroidal spacetime. On the spacetime, we consider the Euler equations and fluid in this regime. Again, dust we don't have to do because we already know due to Jared's specs result that dust is stable. And for the radiation, we know that it's unstable. So we do everything in between now. And what we're showing is that if we start with sufficiently small initial data, then the solution is future global, and it's also remaining close to the homogeneous solution. Of course, in this case, we always have to rescale appropriately because in respect to the space-time, the fluid is, of course, decaying. That's something that you can already see in the background. So you have to sort of normalize your solution and then study the deviation from the rescaled solution. Okay, so maybe just to point out why this works is quite... so originally we proved it in a different way, but now our student has found a sort of, let's say, simpler explanation of why this is true in the more standard variables, let's say. So the reason the reason for stabilization in this situation is the following. So what we study is, let me say, we take phi, and phi is the rescaled fluid potential, and then we write down for this rescaled fluid potential, let's say, standard L2 energies, as we do for the wave, but with a little modification that here we also add the deviation of the fluid potential from its background value. So CH is just, let's say, a constant. So in the background, phi is equal to CH. We add this little modification. And then what we see is if we write down, let's say, the first order energy, so this E0 of phi, which is, let's say, just a standard L2 energy, and we look at the energy estimate that we get from the wave type equation, then what we see is that on the right-hand side, we do not get back our full energy. We get only back a so-called parallel energy, which is only a part of this energy, which is this one here, right? So we only get back essentially an energy that contains these two terms. We do not get back this L2 part of this norm, right? So psi L contains an L2 part of this phi perturbation. And so such an energy estimate will not give you decay, but the reason why we have orbital stability in that case is that, well, here it comes with a good sign, and then any other perturbation, any other term that appears in this equation, let's forget this last one for a second, you can again estimate only by that parallel energy, right? So that's the key. So then if you have a negative term here that sort of you can use then to absorb all the other positive terms, that's the reason. And now see that this must break down for the radiative case, and it does, because for the radiative case, this kappa, you can see here we can choose it between these two values, but for the radiative case, k is equal to 1/3, and this exactly breaks down. So kappa is 0, we have no term to compensate, and this is exactly why this is consistent with what Jared Speck observed in his first result on the shock formation, okay? But here in this case, we have a positive k, and that means that this term can be really used to compensate all the perturbative terms, which are here contained the C epsilon times E parallel. And this term is just an artifact because we wrote this down for zeros. All for higher order, this can be absorbed also in that term, okay? So we see that we can only expect from such an estimate orbital stability. So the energy remains close to the initial value, okay? That we can show, but this is exactly what we need to show the future global existence for the fluid, right? So that's essentially the proof in a nutshell. And it's interesting because we will see this structure again also in the more, let's say, difficult results that we've proved eventually. So the fluid seems to have this regularity nature that if we define the standard energy, we take a time derivative, we get back a part of the energy with a favorable sign if the space-time expands fast enough, and if we're, in this case, not radiation, and some terms that can be absorbed by it. That's how these energy estimates work. Yeah, but I cannot go too much into technical details. That's the first result. So the second result is, now we want to consider back reaction. And in the case of linear expansion, the only model that we can study in this case is the Milne model, because the Milne model is the only linear expanding vacuum solution that we know. Okay, and remember, for other topologies, we either get recollapse for positive curvature or we get metal domination, which is decelerated. So that's not the linear expansion rate. If we want to study linear expansion rate coupled to Einstein, we need actually to pick the Milne model. It's at the moment the only candidate we know that is vacuum stable, and it has the chance to be also stable for Einstein-Euler. And sorry, here I made a little mistake. This is not for Einstein-Euler, not yet. This is just for Einstein dust. So K equals 0. Okay, should have written this. Okay, so I don't really, well, let me make a few remarks on how this works. Again, so this here I recycle a few slides from I think that some of you have already seen, just to remind you on how Milne stability works. I go through this quickly because some of you might know, and it's not relevant for how the dust works, but I want to mention it nevertheless quickly. So remember, Milne model is this linear expanding model where we have a spatial Einstein manifold with negative Einstein curvature. It exists in all dimensions. Again, we are interested in the 3+1 dimensional case. So this vacuum stability is originally due to Anderson-Moncrief, and there is a very brief mechanism that shows stability in the vacuum case. Let me just run you through this to remind you and maybe to motivate you to look at this yourself, because I think it's a fantastic playground for problems to study when you want to study Einstein coupled to other meta models, for instance. So again, this problem is studied in the so-called CMC-SH gauge, so which takes this particular form, which casts the Einstein equations into an elliptic hyperbolic system. Since we are in the cosmological setting, we have expansion. We need to normalize our variables, which we do here by the mean curvature time function, to get variables that do not have an overall growth anymore. And then we introduce a logarithmic time, which gives us sort of some exponential terms in time that should not irritate you. We still have the case of linear expansion here. It's just a different time variable. And when we do all these modifications, then Einstein equations get a nice elliptic hyperbolic form here. Two evolution equations for the metric, for the rescaled metric, and the trace-free part of the second fundamental form. G is equal to the background metric, to the rescaled background metric in the background, and sigma should be actually 0, so sigma should decay. And to control lapse and shift, we have two elliptic equations. And in this, due to our gauge in the scenario, these Ricci tensor terms here actually give rise to a nice elliptic operator, a variation of the Einstein operator. So we really can see the wave equation in this second evolution equation here. Now, this wave equation we take as the basis for defining, again, standard L2 energies. So here, let me just drop the meta terms for a second. So this is how it would look like when we drop all the perturbative terms. And so then how we show stability for this, for the system is that we define, based on this nice elliptic operator, standard, let's say, L2 energies. That's just a sophisticated way of writing them, with a suitable indefinite correction term that, if the constants are chosen nicely, gives you a very clean and nice energy estimate for this energy that controls the perturbation. So this is this correction term. And in that case, you see you have a nice energy estimate here in the second blue box, where again, if I turn off the matter for a second, we really see that this immediately implies vacuum stability. Yeah. But of course, in the case that we want to study now, in this particular part here, dust, and eventually for the fluid, we have to turn back on those matter terms and make sure that they decay fast enough. Yeah. But I will not talk any more about Einstein equations in the following, because let's say you have to believe me, but if you can control the matter terms in both cases, both for dust and also for the fluid, then their contributions into the Einstein equations, they work fine. So they do not decay slower than the perturbations that we have from the Einstein equations, from the geometry itself. Okay, so that's not the problem. The problem is, how can we handle the dust and the fluid themselves? How can we show that they remain small in the suitable Sobolev norms? That's really the main issue. Okay, so that's what we need to understand. For this first result, we need to understand how do we handle dust in Milne. So the dust equations are interesting because, as we saw initially already for Speck's result, dust decays. So let's say dust remains regular even in very slowly expanding spacetime. So the expansion point of view that we need a lot of spacetime expansion for dust, that seems not to be the problem. What the problem is for dust is that dust has a regularity issue when you want to control it. And let me just briefly point this out. If we look at this equation, these equations naively, then we see the following here. So we see, if we look at our Einstein equations, just here, let's say, for instance, the Lebesgue equation, or more instructive, the evolution equation of the second fundamental form, and we see that the second fundamental form, and here the dust variables, the energy density and also the velocity, they appear on the same level of regularity in the Einstein equations. So when I want to estimate sigma, I need rho and u on the same level of regularity. On the other hand, if I look at the fluid equations, then what I see is that, well, if I want to control u, then let's say this is the term one can deal with by integration by parts. This is a natural geometric term. That's not the problem. And then we see on the right-hand side that we need sigma again. So that's consistent with what we see here. They seem to appear on the same level of regularity. However, if we want to control the energy density, then we see on the right-hand side, suddenly we have derivatives of the fluid velocity. So there is a loss of derivative happening here, and there is no way to naively close this without a nice idea on how this can be overcome. And thankfully, this idea is, as I discussed, is not due to the expansion rate of spacetimes. This is a regularity problem. So it was also a problem in the exponentially expanding regime. And this was already solved by Speck and Hutchich, as I mentioned in the introduction. And they have had a very nice idea on dealing with it. Namely, what they did is they introduced the so-called material derivative. The material derivative is, I think, a term that has been known before, but they used it here in the context of Einstein equations. So the material derivative is the derivative that, in this case, appropriately rescaled, appears on the left-hand side of the Euler equations. And so you see, if you rewrite your Euler equations, you see that the left-hand side just appears here as a material derivative of the two variables. And when you look at this like this, then you can see, well, now I can use these Euler equations as constraints. Whenever I have such a term appearing, I just replace by the right-hand side. And I don't have a generic derivative of these two quantities. And so what one has to do, and we had to sort of translate it to this approach with the CMC SH gauge in the case of the Milne stability, is we have to introduce these operators, these fluid operators, into the norms of the geometry, into the Einstein norms. So instead of writing a top number of derivatives on the geometric perturbations here in terms of this elliptic operator from Einstein equations, one derivative has to have the form of this fluid, of this material derivative, including the fluid variables. Because what happens if you do that is that now if you take your time derivative of these energies and you would run into this regularity problem, what you can do is you can just substitute according to this line here and commute the material derivative inside of your rho, which appears in your Einstein equations, but then not treat this as a generic derivative, but just replace by the Euler equations directly. Yeah, and when you do this, then you do not lose a generic derivative and you can close the whole thing. That's the sort of main difficulty. Since I think I'm already advanced with time, I'd maybe skip the next problem, which is also due to this material derivative here. So there are some technical issues that we had to overcome, but I think it is very specific to this problem. So let me just skip that for the purpose of this talk. Second, okay. So what we know now is, okay, so the dust stability that holds even with back reaction in our diagram. So the point below where we knew without back reaction there is stability, now we know it is also with back reaction. But now we want to know the full line with back reaction. So Milne stability for any fluid that is below radiation. And that is a result which is actually quite recent. And and everybody is involved in this collaboration. And this result was basically two theorems. So the first one is, again, if we take the linear expanding torus, our toy background space-time, and we study now any fluid between dust and radiation, then we have future global existence and smallness of the rescaled solution. But even if we turn on the back reaction and consider now the Milne model and its stability, then we actually can prove in the affirmative that solutions to the Einstein-Euler system, which start close to Milne, remain close to Milne and are future regular, and closing this whole line in our diagram. Now this let me make a few brief remarks on this proof, because I think it is also interesting to see how one can move on from there, or maybe also how one cannot. Remember, we looked at the result of Speck initially. We saw that he had this integral over the scale factor that needed to be finite, and we see that this criterion exactly breaks down for the linear case. Now we had to do more to make it work here, and similarly here we see where our methods break down as well. But first, let's see where they do work, and they do work in the regime of linear expansion. So here we have to be a bit more technical, and we have to sort of resort to this Fuchsian analysis, which is a method that Todd Olinik initially, let's say, from my point of view, invented. But I think the Fuchsian methods, they did exist before, but he brought it to the study of the Einstein fluid system in the exponentially expanding regime. And so we see from here that this method is also it is also successful in the linear regime. And what you do here is you introduce a new time variable where at t equals to 0 we have time like infinity, so that's the state of expansion, and we do a conformal transformation of our metric, and we rescale accordingly our quantities again, so that they vanish in the background. Here, the new fluid density and the fluid velocity. And the problem is then if we just write down the system in those variables as we did initially for our first result, then the problem is that we see terms that appear that are they don't decay fast enough. Let's put it this way. They don't decay fast enough. But then there is a somewhat miraculous another coordinate transformation, which we see here, to a new set of variables, psi and little z I. And this transformation, there's basically not much to explain at this point why it exactly works, but it's a miracle and it does work. And when we transform our equations, we get a evolution equation that has this form. And so here, these are our new variables. We want to show that these variables remain small. So again, what we have to find is, remember, initially I told you that when we write down an L2 energy for a fluid, what we observed is that we do not get a full decay-inducing term. We get a good term with parts of the energy, and then we see that there is another term, that all the other terms can actually be absorbed by that term. So likely, this is again what we will see here, and this is indeed the case. So what happens here, if you look at this first order system for these new variables that we see, I mean, I don't want to walk you through the details. There's two important things. All the perturbations are quadratic in the perturbation z. That means they decay faster if z decays than linear terms. That's what this transformation does. And the second thing is, this term here on the right-hand side is exactly this compensating term. Why? So to some extent, to one extent, it consists of a projection operator pi that tells you you don't get the full variables back, but you get a part of the variables back. Again, this is the idea of this parallel energy. You get a part back. This part has the right sign. Okay, this part has the right sign. Why does it have the right sign? There should be a minus here, but remember 1 over t is exactly going sort of in the other direction. So here a plus sign is the right sign. And this b is here the identity with a prefactor, and we see a very nice thing to again assure that we're seeing a sharp estimate here. We have k to the -1, -3, and we see again for radiation this becomes 0, meaning the term that saves our day vanishes for radiation exactly as it should be, because there we do not expect stability to happen, right? So this really reflects what we like to see, yeah? This nature of getting a good term back, but just not the full energy. Now we see in this, we see from the structure that this Fuchsian system has a structure now where we have a theorem that can be applied that implies that the solution that we want to control here with this or with the system of equations indeed is future global. Okay, but the real cause for this is this good term on the right hand side and the fact that the other terms have the right structure. If we consider the fully nonlinear case where we also have perturbations of Einstein, and now on the Milne background where we do have curvature, things get a bit more complicated, but the overall structure remains the same. Now we take another time variable, the one for Milne, so that again has the right intuitive direction. So we want a minus sign here. Again, the structure has essentially the same, the equation has the same structure as before. We get again this structure that we know from the parallel energy and the good term on the right-hand side. And here we have to work a bit more because again, we have curvature. And when we have curvature, then when we commute, of course, there are additional terms that appear in our energy estimates. And again, if we look at our energy estimate eventually, let me go to the next slide, maybe it's a bit more clear. We see we have here to correct our energies by some lower order terms to make those other terms disappear. Again, it's a standard trick in this business. We have seen it before for the Einstein equations as well. Here, this is how it works. You can do the same thing. And then eventually you get an energy estimate, which here at the, if you put in top order here for your energy estimates, the plus one on the slide, we see again, we have our familiar 3 minus k to the -1, which is now this term that vanishes for radiation. But when k is smaller than 1/3, bigger than 0, or well, it doesn't matter, but smaller than 1/3, then this term has the right sign. It absorbs all the other terms, and we can integrate, and we get global regularity for the fluid. You know, so in all three results, the structure of how these energy estimates work are the same. You just have to work more to get them in the more complicated situations. Good. Let me just conclude and then give a brief outlook, and then I'm done. I hope I'm fine with the time. Good. Okay, so let's look at this picture again. So anything that is green here has been understood previously. Now, what we do understand now is this red line. Let me maybe go to the next one. Here we have the instability of spec. Here on all this yellow or orange line up to the bottom, including the bottom point, we do have stability with back reaction. So we see that while the Einstein flow dramatically changes there, the fluid only changes when we go onto this line from the right in this one point all over here remains regular. Okay. Right. So that's sort of what these three results contribute. We can conclude we do understand for linear equations of state now the fully non-decelerated regime, so accelerated and this line. Of course, what would be open also in this regime if we take other equations of state, for some there has been done something, for others not. But the main regime that is open is essentially this regime. So the decelerated regime. In the decelerated regime, we do have these matter-dominated attractors like the Einstein de Sitter universe, which is believed to be mode unstable according to the Sachs-Wolf instability. Again, one has to translate this to this context, but sort of there is a good evidence in some recent works as well by some colleagues that this might be unstable. The reason why this is very sort of is probably very difficult is because if you start now to perturb the matter away from homogeneity, this couples immediately into the expansion rate. So the spacetime expands differently in different points, and that makes the whole thing very non-uniform and hard to handle. But of course, something that we have been trying and starting now is to look at this regime here in the decelerated regime and to look at this numerically in some collaborations to see and get some indication of what might happen there. But our methods, for now, I couldn't point this out in particular, but our methods, the structure of our energies, and so they immediately fail if you go to this side. Unless, of course, you never know, maybe there's a nice other transformation that can make it work. But for now, this is really where things get interesting, as they should. But what we know is, so shock formation from arbitrarily small data either occurs in this regime here on the red point or to the left of this orange line. That's where we stand. So thanks a lot for your attention. I hope this was somehow clarifying what we know about relativistic fluids in cosmology at the moment.
Thank you, Professor. This was a great talk and really clear, really clarifying. So now is the time for taking questions. So in the audience, if anybody has any questions, please go ahead, unmute yourself and ask. Okay, then I guess I'll ask a couple of questions. That's
Sure.
all right. Yeah, this was a really nice talk, really clarifying, really clear, and yeah, so in this, you mentioned this terra incognita, this is kind of open and it's like really difficult, right?
Yeah.
Yeah, so is that like, this I saw like this in one of these Jared Speck's like article, he kind of advocates this Christodoulous energy current to define energies.
Yeah.
Is that like, useful to study this sort of stability problems, like, instead of like, suppose I don't want to define those the standard energy that we have and the correction term, like that you suppose I wanna construct the energies by means of those energy currents. Are they basically the same thing, like other way of doing things, or like?
So I think he used this for essentially all this green area that I have here on my slide. This is where, from what I remember his paper, that's what he basically used to show stability there. Again, I think in some sense is a very elegant version of an energy estimate that is geometrically more natural. So it's certainly a technique that one should keep in mind and try to work with. We have looked at those sort of ideas. There's always a natural estimate for those currents that you can write down. Right. Whether it can do something in the decelerated regime, well, maybe. For me, it's basically, let's say I'm not even at the point of methods, or we in our collaboration are at this point not even at methods to prove stability. For us, it's even too difficult to decide what to believe in, because let's say if you go very much to the left of this area here, so very much to let's say you go to this line, you know, by Christodoulou you have shocks, and if you go to the left, things, if you look at it numerically, they look very much like shock formation. But in this regime more to the right, it is difficult, it's not so clear. So something you would hope probably is that there is some transition line somewhere in between, but I'm not even so far ready to guess what that could be, right? So at the moment, I don't even know what to conjecture. Let's be very honest. This is there we need some like lucky insight on this problem to get a foot in the door, I would say. But if, then certainly energy currents would be a way to maybe understand something that we cannot understand by energy estimates. Yes, I do agree.
Yeah, these are difficult problems, right? I mean, they're super difficult problems, like mathematically, yeah. But yeah, this is very interesting, like, and clarifying, you know, there's like some even in this terra incognita, there's like something interesting might actually happen. Like there might be some boundary or something, but like it's very difficult to conjecture. Like as you said, like okay,
that would be nice. Yeah, that would be very nice to have some structure there. Yes.
Yeah. Wow. Yeah. Thank you again for that was really clarifying talk. Yeah, I learned a lot of things.
Great. Well, you see, there's many open problems, so we're looking forward to new results.